When faced with situations where we don't know what to do or problems that we're unable to solve, we'd like to discover ideas that reveal effective courses of action or solutions. Often these ideas seem to come from nowhere, although usually they do so after a long period of preparation and struggle. Is it possible to find strategies, ways of thinking, educational styles, and even environments that foster good ideas and discoveries? People have written about this issue from a variety of viewpoints. In this and the next lecture, I'm going to borrow insights from two books that were written 2 decades apart by authors from very different backgrounds. One book is titled Discovering, published in 1989 and written by immunologist Robert Root Bernstein, who's written extensively about creativity and science. The other book is titled Where Good Ideas Come From, published in 2010 and written by Steven Johnson, best-selling author and founder of influential websites Outside.in. The two books contrast with one another to some extent, but they also have important themes in common. Good Ideas doesn't cite or mention discovering. Discovering focuses exclusively on creativity and discovery in science, whereas Good Ideas spans science and technology. Discovering dwells more on the individual, and Good Ideas more on networks and environments, although neither book neglects any of these topics. Where they do overlap, for example in discussing the kind of thinking that generates new ideas, they approach the same topic from different angles. These differences will enrich our understanding. Let's begin inside the individual thinker, and we'll branch out from there. If Louis Pasteur was correct in his assertion that chance favors the prepared mind, what kind of preparation seemed to be effective? Discovering points out that the context Pasteur seems to have intended is when an unexpected observation arises, so he appears to be saying that if you happen to see something new, it will become a genuine discovery only if you can understand what you're looking at. A problem with this advice, and the scientific folk wisdom surrounding it, is that it pulls us in 2 opposing directions. The most obvious advice to you, the would-be discoverer, is to acquire deep expertise in your speciality, the kind that often is said to require 10,000 hours of deliberate practice or experience. And this does seem to be what Pasteur had in mind, and it accounts for several of the discoveries he made. His own accounts refer repeatedly to assiduously accumulating relevant facts, candidate theories and hypotheses, and thus being able to gain insight into any new, unexpected observation by drawing on a vast repertoire of knowledge and ideas. However, the second kind of advice is that the best preparation for the mind is some expertise in one or more areas outside of the domain in which you're working. That can be achieved in at least 2 ways. By having intellectual hobbies outside your speciality, or by setting to work on a problem outside your speciality. Johannes Gutenberg invented the printing press by combining the existing technologies of a screw press for crushing grapes and the metallurgy of movable type. The physicist Luis Alvarez is most remembered for his contributions in geology, his theory of mass extinction by meteor strikes. Jacobus van 't Hoff could make contributions to organic chemistry, thermodynamics, geology, and oceanography because he had both taught all of them and done research in all of them. The borrowing from one area and adapting it to another mimics a type of adaptive process for which evolutionary biologists Stephen Jay Gould and Elizabeth Verba coined the term exaptation. Exaptation occurs when a feature that has been optimized for one function becomes hijacked to serve a different purpose. For instance, in one of my papers, I borrowed a statistical model from financial statistics used for modeling accumulated expenditures or losses in financial institutions such as banks, and reformulated it to be used in psychology to model accumulated bouts of attention to stimuli. For a more far-reaching example, consider obstetrician Stéphane Tarnier's invention in the late 1870s of incubators for prematurely newborn humans, based on the ones he'd seen in a zoo for newborn chicks. That simple exaptation has saved countless lives since. What about insights or hunches themselves? How can we make them happen more often? Discovering provides 4 answers to this question, and the first 3 are advice about how to generate the kinds of novel, surprising events that can lead to discoveries. First, the Kettering principle. Novel events are elicited by active curiosity and play. Alexander Fleming's discoveries of lysozyme and penicillin are good examples. He literally played with microbes, and both discoveries arose from accidents resulting from play. Second, the Disraeli principle. Novel events elicited by novel actions and experiments. Konrad Lorenz, the famous ethologist, kept numerous birds, fish, mammals, and reptiles as pets, getting to know them intimately and observing their behavior constantly. The discoveries that led to his Nobel Prize stemmed primarily from the often impromptu field experiments he conducted on members of his menagerie. Third, the Pasteur principle. See novel things in mundane or even discarded observations. In 1889, Oskar Minkowski removed the pancreas of a dog to study its role in fat digestion. The dog subsequently urinated on the laboratory floor. The urine attracted flies, and this was spotted by a lab assistant who brought it to Minkowski's attention. Minkowski analyzed the urine and found that it was loaded with sugar, and this in turn led to the insight that pancreas secretes insulin, which regulates sugar metabolism. Minkowski and his lab assistant had stumbled upon a fundamental insight into diabetes. The fourth piece of advice is somewhat related to the preceding three, but on a different dimension. Dare to err. Linus Pauling famously declared that the key to making discoveries in science is trial and error. Just have lots of ideas and throw away the bad ones. But most of us are strongly socialized against making errors. Writing a grant proposal in science is largely an exercise in demonstrating that you're able to completely forecast how your experiments are going to turn out and that you're never going to make an error. Returning to Louis Pasteur again, he embarked on a lengthy series of misguided experiments in the belief that there was an asymmetric force behind things like polarized light, electricity, positive versus negative charge, and magnetism, north and south poles. In the midst of these failed experiments, he discovered that a fermentation process occurring in a right-handed form of tartaric acid could not occur in its left-handed form, that is, asymmetric fermentation. Another reason to have many ideas is that where they disagree or conflict with one another, you can design experiments or tests to pit them against each other. An experiment that is designed solely to test, or worse, to confirm, one hypothesis is bound to fail in one of two ways, no matter what the outcome is. First, if it confirms the hypothesis, you've discovered or learned nothing, because the hypothesis anticipated the experimental outcome. If it disconfirms the hypothesis, then you're stuck, not because the results are unexpected, but because you have made no preparation for interpreting the unexpected. In testing multiple disagreeing hypotheses, no matter how the experiment turns out, it will be informative and you will learn something. Having lots of ideas is one thing, but are there ways we can increase the likelihood that they will be correct or pay off? Oddly enough, both discovering and good ideas point to the same essential role of error and sloppiness in the generation of hunches that turn out to be right. The key idea is that if every action you make is carefully planned and controlled, you'll only see what you expected to see and nothing new will crop up. Biologist Max Delbruck advised students to be sloppy enough that something unexpected happens, but not so sloppy that you can't tell what happened. Of course, there is a fine line between enough and too much error. Astronomers Arno Penzias and Robert Wilson observed what they thought was static due to an undiagnosed fault in their radio telescope, and for more than a year, before a conversation with a nuclear physicist colleague alerted them to the Nobel Prize-winning insight that this static was evidence of cosmic background radiation from the Big Bang. Good Ideas brings in an additional claim about how to make hunches more likely to pay off. Those that incubate over a period of time are more likely to bear fruit than those that are a sudden bolt of lightning type of insight. The argument for this claim is that slow hunches stand a better chance of being tweaked, supplemented with other hunches and information, and thoroughly tested than fast hunches. A classic example of a slow hunch is Tim Berners-Lee's invention of the World Wide Web. His own account of the process spans more than a decade, starting with an attempt to keep track of personnel and research projects in a Swiss research lab via a novel kind of database, proceeding through various developments and elaborations and culminating in the hypertext language-based method of connecting documents stored in different computers. Finally, a well-known but underused aid to discovering things or solving problems is giving up. The mathematician Poincaré's famous account of this ploy has him struggling for 15 days to prove that a certain class of mathematical functions do not exist, and then having the first example of such functions suddenly occur to him one evening when he breaks his normal routine by drinking black coffee and is unable to sleep. Subsequent breakthroughs visit him when he is boarding a bus, and later when walking along the seaside. Being able to recognize when you're stuck and knowing when and how to give up on a problem, temporarily but genuinely, are skills that increase your likelihood of finding solutions and discoveries. These tips for making discoveries and having good ideas all have something in common. They all focus on the thinker and her or his thought processes. There are only a few hints of an equally important source of discovery and good ideas, the thinker's network or of peers or colleagues, and the intellectual culture in which the thinker is immersed. The history of discoveries bears witness to the importance of those networks and cultures, and its most obvious sign is that so many discoveries are made nearly simultaneously by multiple thinkers. For the theory of natural selection in biology, we have Charles Darwin, Alfred Russel Wallace, and others. For the calculus, we have Newton and Leibniz, and simple thought experiments suffice to show how crucial culture is. Imagine a Mozart, born into a society with no pitch-definite musical instruments, or a Tim Berners-Lee born even 20 years earlier than he was. So in the next lecture, we're going to shift our focus from the individual to their network, community, and culture.